This is Sean Blair reporting for ESA Web TV. I'm here in a clean room store in ESA's ESTEC Technical Center in the Netherlands, and kept within here are a few tiny pieces of some of the rarest, most precious material imaginable. It's come a very long way to get here. Japan's Hayabusa spacecraft was the world's first mission to retrieve samples from the surface of an asteroid and return them to Earth. It nearly didn't make it. Launched in 2003, Hayabusa was damaged by a solar flare during its trip through space, finally reaching the rubble pile asteroid Itokawa in late 2005. When Hayabusa deployed its mini lander, it was lost in space. So instead, Hayabusa itself made attempts to gather samples, firing projectiles to gather up dust into sample containers. At one point, Hayabusa even crash-landed into the surface while out of contact with Earth. But the asteroid's low gravity meant Hayabusa was still able to head back to Earth, although it had to be nursed along with frozen pipes, leaky propulsion and failing batteries. In 2010, unsteerable by the end of its 6 billion kilometre journey, the crippled spacecraft approached Earth's atmosphere like an asteroid, breaking apart. Hayabusa's sample container, however, was heat-shielded and parachuted back to the Woomera test range in Australia. Until scientists retrieved the small container, they had no idea if it actually had any asteroid samples inside it. And when they opened it, they still had no idea at first. It seemed to be empty. But scraping the sides of the container, followed by detailed scanning with an electron microscope, revealed 1,500 tiny particles that were of extraterrestrial origin. Extremely precious, these Hayabusa grains have become the focus of intense scientific study around the world. And 3 of them are currently here, at the European Space Agency's ESTEC Technical Center in the Netherlands. I'm here now in the lab with space environment researcher Fabrice Cipriani, who's been leading the study of the grains. So Fabrice, where did they come from? How did we get them here?
Well, actually we built up a consortium made of researchers from ESA and also from teams of INAF in Roma and the Partenopeo University in Napoli, to propose an original study focusing on the electrostatic properties of those particles.
And that's different from usual. Normally people are interested in what the materials are made of rather than what they do.
Exactly. So most of the studies are aimed at measuring the mineralogy, composition, basically the fundamental ratios of compounds which helps to date back the grains from the origin of the solar system, etc.
So what's the focus of your research?
Asteroids do not have an atmosphere, and as a result their surface is directly exposed to incoming fluxes of charged particles coming from the solar wind, coming from the sun. So those charged particles, they deposit charges into the material. Asteroids outer surfaces are layers of very fine particles, which dimensions ranging from microns to centimeters typically, which are held together by gravity but also by cohesion forces. And on the other hand, they are a bit loose due to the acceleration, due to the rotation of the body, but also due to those electrostatic forces which are repelling particles from one another. And the focus of our research is very towards understanding a bit more or characterizing a bit more this type of interaction, electrostatic interaction, and the impact of those interactions in terms of regolith structure is that, for instance, the porosity or the density of the material can be a bit different from what we think it is if we do not include this component of the forces.
So future designers of things like drills and instruments, they need to know this to actually design.
For instance, that's a component they might want to be aware of, and it's especially true if you go a bit deep in the layer, which is most affected by more energetic particles. But the way the layers are held together, especially if the asteroid body is very small, is affected by such effect. So the people designing drills might be interested to know that.
And could it actually give a landing spacecraft some kind of electric shock?
Yeah, well, so there are various effects, let's say. In general, the risk might be low. If you bring those two objects close together, you think they might trigger some static discharge. But the amount of charge, or let's say energy needed to do that is not very is not high enough in the standard situation. The solar wind particles are not very energetic. Now, if we think about situations where we have coronal, for instance, solar storms with higher energy particles, then maybe you can build up a bit more gradient of potentials leading to some risk. And other aspects are indeed the way those layer, the outer layer and those particles can separate from the surface, being driven by electrostatic force, which somehow overcome the gravity, which sticks them, which helps holding the whole structure together, and they can be lifted and transported. And this is something, for instance, Apollo astronauts thought to have observed, but on the moon actually this has never been really confirmed. At least the Apollo missions are good examples of how grains can adhere to materials, and this is also due to their very peculiar shapes and the way the static, let's say, they behave in terms of static electricity and the way they interact with materials.
So what do the grains actually look like?
First of all, they are very small. Well, the samples we have are about 10 micrometer or 20 micrometer in diameter. The Hayabusa samples go up to several hundreds of micrometer, but we have very small ones. Also, when you look at them, they have a very inhomogeneous structure. They are very sharp edges. This is because they've not been weathered by water, eroded by water like on Earth, or friction together in the same way as Earth's particles are. And also you have micro cracks on the surfaces, so they're not like one block, they're cracked. And also you have micro craters or nano craters actually on them, which is also a witness of the fact that they've been exposed to the outer environment. A bit like all bodies in space, all planetary bodies in space have craters at their surface.
What do you do to them to test them?
Yeah, what we do is try to reproduce a bit what we have in space, although we can't reproduce, for example, solar wind in the chamber, but we try to bombard them with electrons and measure the amount of charges which are accumulating on the surface and how those charges distribute on the surface. And this is something which has never been really measured at this scale, at least on asteroid material. There was some testing done on Apollo samples. But in fact, because we don't have a lot of, well, actually we have very few of those particles, we also play with more standard material, which are like lunar analogs, for instance.
Like simulants.
Like simulants, lunar simulants, exactly. And we can at the same time play with full layers.
What's it actually like to work with the grains themselves? You have to be very careful, I guess.
Yes, we are we're extremely careful. From the time we received it, we've been thinking for quite a long time, I would say maybe 2 years, of developing a method which allows to handle them in a safe way, preserving at the same time their outer shape. Because unlike indeed what most laboratories do, because of the type of measurements, we do not want to embed them in some aerogel, or we don't want to press them into a support and then cut them to investigate their internal structure.
And you want to give them back to JAXA?
Yeah, indeed. So what we aim for at the end of the study is to safely bring them to give them back to JAXA. So hopefully, when due to this method of handling, they will not have been altered or destroyed by our analysis technique.
Right. Well, thanks Fabrice for showing us around, and indeed thanks to JAXA for being so generous in the first place. The good news is these grains might become a bit less rare in future. A follow-up JAXA mission, Hayabusa 2, is currently in space, due to return with more asteroid samples in late 2020. This is Sean Blair for ESA Web TV, signing off.